Good morning to everyone. Today we will discuss the MSc Physics in semester first, classical electrodynamics, and this is the unit first. Today we will discuss the three important topics. Number one, the electrostatic potential energy. Second one is the energy density, and third one, the capacitance. This is only the upgradation of the UG classes contents. So start from the definition of electrostatic potential energy. What means of electrostatic potential energy? The electrostatic potential energy of a system of a point charges is defined as the work required to assemble this system of charges by bringing them closer from infinity to the system, or the total work done by an external agent in bringing the system of charges from infinity to the points. Or in simple language, we can say to assemble a system of the charges, the energy required or the work done by the system or any external agent, that is called the electrostatic potential energy. This is the stored energy of the system. Now, how we can obtain the expression of it? If a point charge is Qi is brought from infinity to the point xi in the region of the localized electrode described by the scalar potentials phi at reference, we have considered phi potential is 0 at infinity. Then the work done on the charges, hence the potential energy given for this charge system is equal to the Wi equal to the Qi phi xi. Phi xi, the potential at the xi, or you can say work done on a unit test charge to move from to the infinity to the point, that is the definition of the potential. So, we can write Wi equal to the Qi phi xi minus phi infinity, because from one point to other points the potential difference is this one, and we have considered as the infinity as the reference point, and where we have considered the potential equal to 0. So, the W equal to the Qi phi xi, where Qx phi xi is potential produced by the remaining charges, which is the function of the xi. Here the phi xi, the potential due to the all point charges except the one at the Rj, and it is equal to the phi xi equal to, we have known very well that V equal to Kq by R. K is 1 by 4 pi epsilon naught, Q is the sum of the all charges. So that is from j equal to 1 to n minus 1. Why we consider n minus 1? Because one charges at the ith position. So that is, we can write Qj summation by the xy minus xj. Here Q1, Q2, Q4, Qni, that is Qj, they are the charges except the Qi. So the potential energy on the charge Qi equal to Wi Qi 4 pi epsilon naught summation j equal to 1 to n minus 1 Qj divided by x minus xj modulus of it. The total potential energy of all the charges due to all forces acting between them, then we can write the summation of the all potential energy of the different charges, W equal to 1 by 4 pi epsilon naught sigma I equal to 1 to n, and also the j from 1 to n, and we have considered I is not equal to j. Qi Qj xi minus xj, because we know very well that potential energy is Qi and the work done is the Q2 is W equal to Q2 phi I R1. Similarly, the charge potential generated by the Q2 at the charge Q1 is equal to U equal to Q1 phi 2 R1. So the total energy of the system is the sum of these two, add n divided by 2. So for the n charges system, we can write here the charges are the Q1, Q2, Qn at the position at the x1 to the xj. So the net charges and have the potential energy U equal to 1 by 2 sigma I equal to 1 to n Qi phi Ri. Here we have used 1 by 2 because the each term is counted twice. So Ue equal to 1 by 2 4 pi epsilon naught sigma I sigma j, I is not equal to j Qi Qj xi minus xj. So this is the potential energy of the system of the charges. Now if the charge is not in discrete form, it is in continuous form and like the volume distribution. So if they are the charges rho xi dash and they produce the charge of certain point at the rho xi, then the W equal to 1 by 8 4 pi epsilon naught double integration for the volume rho xi divided by x minus xi, and finally we have write the W equal to 1 by 2 rho x by xi dV. The alternate expression for the electrostatic potential energy in the terms of the electric field. The energy is being stored in the electric field surrounded by the charges. So we can write by the Poisson equations the del square phi equal to minus rho by epsilon naught. So the rho equal to, that is the volume charge density, equal to minus epsilon naught del square phi. So the net energy of the system 1 by 2 rho pi x dV. In place of the rho we have to substitute in form of the del square. So W equal to minus 1 by 2 epsilon naught integration of the phi del square phi dV. Here we have write del phi equal to minus in del of the del phi equal to minus del dot E. Now to expression this one we can write in del phi, we can write del square phi की जगह हम लिख सकते हैं minus del phi del E. So the epsilon naught by the phi del E dV. Now there is the identity we have using that the del of the A vector dot B, B is the scalar quantity. So the del A vector plus B and the A vector del dot B. And so the B del dot A equal to the del A dot B minus A vector del phi del can say B. So using this identity we can write W equal to 1 by 2 epsilon naught integration for the volume, and this is the del of E vector phi dV minus E vector del phi, and we know very well that 1 by 2 epsilon naught the phi E, because by using the Gauss theorems we can write this is in form of the aerial integrations 1 minus 1 by 2 epsilon naught E minus के साथ में dV for the all space, and this is for the boundary of the space. So if the boundary at the infinity, then we can write if pi is inversely proportional 1 by r is directly proportional of the r inversely proportional of the r square, and the d is directly proportional of r square. So finally we can write this is 10 to 0 for the boundary of the space, and for the all space we can write this is the final answer W equal to 1 by 2 epsilon naught magnitude of the E square dV. This is the integration all over the space, and the energy density is energy stored per unit volume, that is U bar equal to energy density 1 by 2 epsilon naught E square. So what are the conclusions? The energy is stored in the form of the field. The principle of the superposition is not valid for the electric field because it is then quadratic in nature. So we can write the net electric field E equal to E vector equal to the E1 plus E2 vector, so the E square equal to E square plus E2 square plus twice E1 vector E2 vector. So using this one we can obtain the energy density for the total system, that is 1 by 2 epsilon naught E square dV 1 by 2 epsilon naught E1 E2 का whole square, and using the summation 1 by 2 epsilon naught E1 square plus 1 by 2 epsilon naught E2 square plus 1 by 2 epsilon naught twice E1 E2 dV. Here the first two terms are the sharp energy of the first and second, and the third terms is the interaction due to these two electric fields. So it is called the interaction energy. Now the last topic, that is the capstans. What means of the capstans? How they are used? For a system of the n conductor, each with the potential Vi and the total charges Qi, where I equal to 1 to n in the otherwise empty space, the electrostatic potential energy can be expressed in terms of the potential alone and the certain geometrical physical quantity, the coefficient of the capacity. A device which can store energy is called the capacitor, and the capacitance, the capacity of the device to store the energy, is called the capacitance. It is equal to the ratio of the charge stored to the potential between them. So C equal to Q by V, that is coulomb per volt, that is farad. It is purely geometrical quantity determined by the size, shapes and the separation of the conductors. So the potential on the ith conductor is the Qi equal to the sigma 1 to n Cij Vj. Vj is the potential due to the different, and the Cij the interaction between these two. So that is the capacitance of the capacitor. So the capacitance of a capacitor, the conductor, is therefore the total energy or the total charge on the conductor when it is the maintained at the unit potential. All other conductors are kept at the zero potential. So for the two conductor system, as earlier we have calculated in the UG classes and in 12th class, the capacitance of the system of the two conductor carrying equal and opposite charges in the presence of other grounded conductors is defined as the ratio of the charge on one conductor C equal to Q by V. So to determine the capacitance, we can write dW equal to the V dQ, V Q by C dQ. So W equal to 0 to W, 0 to Q, Q by C dQ. So on integration we obtain 1 by 2 K square by C. And here if the Q equal to the CV, so W equal to 1 by CV square. Energy is stored in the capacitor. Or the parallel plate capacitor, we know very well that C equal to epsilon naught A by D. Substituting the value of the C and the V in terms of the ED, so we obtain the energy density U bar equal to W by volume 1 by 2 epsilon naught E square. The same expression as we have earlier calculated. So this is sufficient for today. Thank you.